Well, good evening again. I am Dr. Reggie Taylor from the Office of Research and Doctoral Services. And tonight I will be facilitating this bivariate linear regression session. Last night, I don't know if we have any returnees, but last night we did something called correlation analysis. And bivariate linear regression kind of lends itself to that is the next logical progression, kind of, let's say, upwards, in the regression, or correlation line of statistical tests. Give me just a second. So what we'll do this evening is go through some bivariate linear regression concepts and application. And again, I'm going to talk about the objectives, which are, again, the number one objective of my concern is to ease your anxiety about the binary regression test, just as we did last night, ease the anxiety about that particular test. You'll never remember everything in 45 minutes here to an hour. We'll never be able to cover everything possible, on a bivariate regression test. I have taken regression courses that were 16 weeks long, much less we're trying to fit a particular test here in 45 minutes. So again, it's that very broad overview so that hopefully you walk away from this session saying, you know what, an hour ago, I didn't quite understand binary regression, but now I have a good understanding of it. And then as you start reading material and perhaps if you're going to be conducting some regression, things will start, connecting and making sense versus you just starting, from a blank slate. And that's my major focus. And so by doing that, provide a broad overview, very broad overview, and understand how to conduct it in SPSS. And also, we'll look at output and understand how to interpret that output, and then to take that output and turn that into an APA compliant results write-up. Now, like I did last night, if you wouldn't mind, could you please just kind of type in the chat, what drew you to this particular session? A lot of times that aids me in, perhaps in maybe mentioning or addressing something perhaps that I didn't specifically put into this particular session. Are you taking coursework or just for general knowledge or dissertation or, well, whatever the case may be? Still deciding what you're going to do. Okay, all of the above. But what I tell people is, regardless of the reason that you're driven here for this particular section, and I wouldn't even care if you were going to do qualitative research. On your particular topic, you are going to be required to do what we call an exhaustive review of the literature. Meaning, if I'm chairing this study, I'm going to be looking for a mix of quantitative, qualitative, and other methods that we use to address that particular topic, because that obviously leads you to the gap, what's missing in the literature. You have to know what's there, okay? But again, we'll provide some additional resources that kind of will take this session, above and beyond and not say, here you are and this is it. And you'll kind of get an understanding that there's a plethora of resources available and that will be available for you in your quantitative journey. And when I say quantitative journey, I don't necessarily mean that you're going to do a quantitative study, but I mean, you're going to take quantitative courses at Walden. You're going to obviously and undoubtedly read quantitative research and literature and your coursework. So that's what I mean by quantitative journey. There should be something useful here for everyone that's attending the session, okay? And then I'm going to ask if you would be so gracious and kind to complete an anonymous survey that really helps and aids me in developing future sessions or even continuing future sessions of this type. And we'll talk about that a little bit more later. So now, for those objectives, how will we do that? We're going to first talk about something called the scales of measurement, as I did last night. And you're going to see how important that concept is to any statistical analysis that you will conduct. So that's why I always cover that concept. And I think it will better help you understand the analysis piece, especially when we get into SPSS. And so what we'll do is we'll talk about the conditions for using the test. We hear the names of all kinds of tests. Last night we did Pearson's correlation. Tonight bivariate. We may hear multiple regression. We may hear the ANOVA. We may hear the t-test. And obviously these tests don't do the same thing, and they're not for the same purposes or same condition. So one of the things that we want to do is make sure that we understand, the conditions for which this particular test is appropriate. Now, because this is a parametric test, and a parametric test meaning that there are data assumptions that we must address and consider before we actually run the bivariate test, and we'll go into that. And those data assumptions we'll talk about. Then we'll actually look at SPSS, run the procedure live. And then we'll look at the output that was yielded from that procedure and understand how to interpret that SPSS output and take that output and put it into an APA compliant results write-up. Now, when we start talking about the results write-up, you'll see there's a plethora of ways that you can present the information, but I'm going to give you a very safe way that ensures all the required information is included. You may be asked to provide additional information or do some things quite differently, but again, these are the very basics here. We'll talk about, again, some quantitative resources that you'll be pointed to continue your quantitative journey. I'll summarize, and then we'll talk about the quick survey. Okay, so let's get to the matter. Binary regression. What is this test all about? What are we doing? When we say that we're going to do binary regression, the first thing that we need to understand is that we're getting ready to predict something. Predict something. And what we're going to predict is the value of some variable. But that variable, remember, is going to have to be a specific scale of measurement. And now what do I mean by that? In this case, it's going to need to be interval or ratio, meaning a numerical number, a value. For example, we have another scale of measurement called the nominal scale. And our nominal variable is categorical, and it wouldn't be appropriate for binary regression. For example, let's say that gender was one of the variables. Well, gender, of course, would be categorical, perhaps male, female, non-binary, and that's categorical. Membership into one of those categories, and a binary regression is not appropriate for that. So that's why it's going to be very, very important to understand the scales of measurement, because one can easily go into a data set and pick two variables and click some buttons and get some output. SPSS more than likely will calculate something. I will tell you what, it will make no sense. It will be wrong if you've used a nominal variable. Okay, so that's important to understand. And again, it's a statistical technique used to answer predictive questions. For example, a simple question such as, what is the relationship between optimism and satisfaction? Now, remember, we're going to predict the value of a scale variable, dependent variable. That dependent variable in this case would be satisfaction. Okay, based on the value of one scale, again, interval or ratio predictor, and we're going to say optimism meets that. Okay. Now, the word "and," you see I have bolded here, and I'm going to put it in yellow because that's a very critical word. And down here, I left a little footnote that says the word "and" separates the predictor variables from the dependent variable. And that variable that sits to the left, which I'm going to now turn green, always comes first. That's the, excuse me, the predictor variable, okay? The predictor variable comes first, and then the dependent variable comes after that. And that's what we call temporal order, okay? So it's going to be important because we distinguish between independent and dependent variables in this statistical test. Unlike last night when we were just doing simple correlation, we don't really distinguish between independent and dependent variables. We're just looking to see, are these things correlated? Are these things correlated? That's all we want to know. But this test takes it a little bit further and not only lets us know that correlated, but also lets us know that there's some predictability from one number to another. In other words, if I know your optimism score, I can predict your satisfaction score. Now, just think about that in terms of research. You know, what are you trying to predict? What is that problem variable out there, that dependent variable? And you have to have a predictor variable to help you predict and understand that. That could be depression. It could be anger. It could be, job satisfaction. It could be a host of things. But you have a predictor variable that's trying to predict that red word of satisfaction, okay? So temporal order is important. And I'll give you a resource, Tom, to have also that will make that explicitly clear. Now, when we talk about regression, one of the most misunderstood pieces is really, what are we talking about? And what we are talking about are residuals. It's all about the residuals. What do I mean by that? Right now, I'm writing down a number on a piece of paper. It's anywhere from 1 to 10. Now, and I put that into the chat. Now, if you would please humor me and type in or guess the number that I have written down. Okay. Now, with your psychic abilities, you have guessed or you have tried to predict the number or the true value, the true number. Now, what I want you to do now is a little bit of mathematics. And don't worry about pluses or minuses. Just do the absolute value, the absolute difference. The difference between my number and your number, and I'm going to tell you now what my number is, okay? And I'm going to type that in the chat. And my number was 3. Okay? So now take the difference between the guess and the real number and type that in. Okay, fantastic. That difference that you have just typed in is called the residual. That is what regression is about. The difference between an observed value of a dependent variable, in my case, the observed value we know was 3, and the predicted value. Now, when we're trying to predict, it's common sense, right? Aren't we trying to predict as close to the true value as possible? Would you say so? Of course we would, yes. But now, would you want your residuals in terms of regression to be low or high? Think about that. If you could take residuals and put it into a number, would you want it low or high? Fantastic. Low residuals, because that's telling you that that model of data is really close to predicting the true number. The residuals are less. And we're going to look at that in a way that kind of helps us understand that, okay? Now, let's take an example. you're interested in examining if optimism can predict satisfaction. Remember, optimism being the predictor variable, satisfaction being that dependent variable. That would be the problem variable or the topic of your research. So a research question could simply be, and this was the exact same research question that we had last night. Is there a statistically significant relationship between optimism and satisfaction? With the no being that there is no relationship, and the alternative that there is a relationship. Okay, so you can see we clearly identified the variables, and also we have put them in that temporal order that we must put them in. Okay, so now just by looking at that, we know that our dependent variable is satisfaction and optimism is our predictive variable. Just by looking at a research question, if it's presented correctly. Okay, does that make sense to everybody? So let's think about it again now. If we're going into a data set, someone gives you a data set and say, run a bivariate regression, you know that you're only going to use two variables, first of all. Only two variables. That data set could have 100 variables in it. Only two of them going to be concerned. And those need to be scale and numerical variables. And we'll look at that in SPSS. Now, but because regression is what we call a parametric test, there's a lot of assumptions that should be met regarding the data, how the data is shaped, or the distribution or the patterns of the data. The way you can think about this is that, there's a mathematical formula for binary regression. And the mathematicians went into the laboratory. Carl Pearson was one of the key contributors to creating the correlation coefficient. But they came out of the laboratory and says, hey, we have a way to predict things. It works. However, the data must meet certain conditions. It works well under these conditions. It doesn't work so well if these conditions aren't met. That's what the data assumptions are, not the assumptions you write about in chapter 1 that you assume that everyone responds honestly and you assume, this and that. These are assumptions regarding the data, okay? So, but however, in real life, 99% of the time, these assumptions are violated in real life. So what do? Do you throw the data back into the pot and resample again and keep doing that? No. You analyze it. You analyze the assumptions. Kind of let me know, how do the data line up with the assumptions? Do they look okay? If not, maybe we'll make a few adjustments to the data. That's what we have to do from a conceptual perspective. So as you can see under the data analysis, we'll have to assess the assumptions prior to running the binary regression test. Then we're going to tell the reader what the results of these assumption tests were. These are things you have to do for a parametric test. Then let's just say that one of these assumptions is grossly violated. You have to do something. And you're going to tell the reader what you're going to do. You do it. Now the data set is kind of like nice and good to go, and you're ready to run the regression analysis. So keep that in mind. And that is a concept and a process for any statistical test that's called a parametric statistical test. And no, binary regression is not the same. Binary regression is the same as binary logistics regression. Yes, it is. The terminology, yes. Okay, so is everybody good so far? Remember, we have a test, and we need to make sure that the data meets those assumptions, okay? And we assess those assumptions when we collect the data. Now, what are these assumptions? There's 7 of them for the binary regression. Remember, the first one is almost kind of like a requirement. The data should be interval or ratio, okay? That dependent variable, meaning a numerical scale, not an ordinal or an interval, for example, like male or female. You can't do that. Now, that's where the binary regression binary logistics regression would come in, okay? That's where that would come in. But anyway, also, before we run any statistical test, we got to consider sample size. It's very critical, and we have to calculate what the sample size will be based on certain parameters, okay? And we're not going to get into depth on all that, but you need to know that you do that, and there's other sessions that we have on power analysis, but you'll need to know that, okay? Now, also, we want to make sure there's no significant outliers. From regression analysis, we know, in correlation analysis, we know that outliers can significantly skew data, even one data point. And I can use the same example that I used last night. Let's say we're taking the average salary of the company Apple, computer Apple company, of their employees. And let's just say that average salary is, say $70,000, okay? The person you see in the Apple store, the person, working somewhere, doing something in whatever the case may be, that's the average salary. But now imagine if we included Tim Cooks, who is the CEO of Apple. Now imagine if we put that $20 million salary in there with the average of 70,000. Do you know, and you can understand how undoubtedly that would skew the data. So that's an outlier perhaps, and we need to identify that and determine what we would do with it. In a lot of cases, we pull it out. But anyway, we're not going to really dig into diagnostics here tonight. But you need to understand conceptually that this is what needs to be done when you're going to run a regression test, okay? Something called independence of residuals. Remember the residuals? We said that they were the different scores. Remember my true score of 3 and your score, that's a residual. And those should be independent of each other for every observation, okay? And we'll talk about how you can assess that with something in SPSS called the Durbin-Watson test, okay? Of course, linearity has to be assessed. Linearity is assessed by something called a scatter plot of the residuals, okay? And then normality is an assumption. The data should have a normal distribution. But remember now, we are talking about the residuals. A lot of people, when they start talking about regression and start talking about the assumptions, they start looking at the assumptions of the raw independent data, not the residuals. The residuals tell us the pattern of the guess, not the actual score. Remember, what we're doing is taking a difference. Now, how does that difference look? Does that make sense? So you are assessing residuals here. It's very important because I see a lot of studies and individuals are just taking the raw data, the age of a person, and ran all these types of tests and saying it's normal. But no, you need to test residual values. Okay? Does that make sense to everybody? We'll talk about that a little bit more. And then there's something called homoscedasticity, and we'll talk about that in just a second. And again, but you also use the same plots for that, okay? So basically, there are tools in SPSS that answer those questions regarding, has the assumption been violated or not, okay? Is everybody okay there before I move on conceptually of what you do when you start running these tests, okay? We make sure we have the right variables. We make sure we only have 2 of them. And then we start saying, now let me do these preliminary analyses and assess these assumptions. You kind of almost like cleaning and screening that data now, getting it shaped up really good to make it, really fit well. That's the first thing you have to do. Now, let's talk a little bit more about these assumptions because they're so important to understand, okay, and to address them. We should never see a dissertation come through and there's not been a thorough evaluation of the assumptions regarding the test. Sample size, we said, was one of those. Now, what you do is that when you're designing your study, once you know your parameters, you're able to use software to determine what the minimum required sample size is, okay? And we won't get into that, but you would do something called a power analysis. You've probably heard of that term before. You've heard of that term before? So any statistical test requires a required minimum sample size. You won't just say in a dissertation, oh, I only had 14 people. No, that's going to be a very underpowered study. So to prevent that from happening up front, you say, based on what I'm doing, these number of variables and this and that, I will need X amount of people. So then you need to go out and recruit and get that many, okay? Because we know generalizability is at stake when we don't have the right sample, little scientific value. You pretty much, have a useless and meaningless study. So that's a very important thing to understand, that you'll conduct a power analysis, okay? Now, outliers. Remember we said the outliers are critical. How do we find those? Well, you're going to find those in something called the case-wise diagnostics, okay? And that's something that you run in SPSS, and we'll look at that. You can see here in the graphic, the linear regression statistics box. And as you'll see that in the residual, you see that? It even says that. I'm glad that it says that. Even in the, give me just a second here. I want to draw something. You see that even in the box, it says residuals. That's what you're assessing, the residuals. And so for outliers, we're going to make sure that we have something called the case-wise diagnostics check. And you'll see that's where that arrow is, okay? And the outlier is considered anything plus or minus 3 standard deviations from the means or the average, going back to basic statistics. Remember, a range plus or minus 3 standard deviations. And anything that exceeds that plus or minus is considered an outlier. And what you look at is the standardized residual number. And you see plus or minus 3, that's greater than 3, right? 3.4. That tells you this is an outlier, but not only that there's an outlier, exactly which record or case in the database is the culprit, case number 18. So now what you would do is perhaps say maybe, so what I'll do is I'll go back into the data set and remove case number 18. It's as simple as that. That's if that's your decision to keep it. It goes a lot deeper than that, but conceptually, that's what you do. So again, you will look at something called the case-wise diagnostics, and what you will be looking for is the standardized residual value compared to, plus or minus 3 standard deviations. Is everybody okay with that? If you saw that, would you be able to understand now what's going on? If someone were to put this output in front of you, you should be able to say, there's a linear regression ran, and there's an outlier in this data set, and it's case number 18. Do you see that now, everyone? Because that's now what we call interpreting the output, and you're not just looking at this stuff wondering, oh, what does all this mean? Because you should be talking about this in a well-written study. So fantastic. So we've gotten through outliers, but we say there are more, right? So we have the independence of the residuals, making sure that, basically one score is not dependent upon the other. And that's really a design thing. And that rarely happens, but there's a way to test to make sure that we haven't violated that. And that's something called the Durbin-Watson test. Notice this is the same dialog box that we just looked at. So a lot of this is all done from one dialog box. You make sure, remember again, we are looking for the residuals, and we select the Durbin-Watson. Before we had case-wise diagnostics, which was looking for the outliers. So you would really select both of these to cover outliers and case-wise diagnostics, okay? Now, when you get output, what do I look at? Well, obviously, we look at the Durbin-Watson number. Okay, Reggie, what do I compare it to? Well, what you do is a value of 2 indicates no violation, basically. And values between 1.5 and 2.5 seem to be normal, no violation. Has this assumption been violated or not based on this? No. Fantastic. And you move on. You say, I assess the assumption of independence of residual using the Durbin-Watson test. There was no violations. Boom. Let me move on to the next assumption. Now, luckily, these next three, normality, linearity, and homoscedasticity, all are done with just one process, okay? And again, the residuals are normal. Linearity, remember the residuals, and the variances of the residuals should be about the same. Now, what do we mean by that? I am going to jump now to a slide. No, let's just go in order here. Okay. Now, what it is that when you get into SPSS in the linear regression module, there'll be something called plots. Okay. Remember now, we're assessing all three of these at the same time. And we're going to say the Z predictor variable here, we can put into the X. The Z residual, we put into the Y. And it's just going to create a scatter plot for us of the residuals of X against the residuals of Y. We want a normal probability plot to help us assess normality. Does everybody see that? So this is all you're going to do. And then you're going to hit continue, okay? And then what's going to happen is that you're going to get a plot that looks like this. Now let's talk about that. When we say that they are kind of tight together and not spread out, that's what we don't want them spread out. And what we're looking for is something like this. You see how everything kind of fits in this pattern here? Kind of going from left to right, kind of evenly dispersed. You know, the residuals kind of, you know, like that, evenly dispersed. That kind of indicates that, you know, we haven't violated linearity and homoscedasticity. It just kind of tells me that just by visually looking at it. Okay? Now, remember that one case that was an outlier that was case number 18 that was greater than 3.5? That might be it right here. You see? That's probably the 3 point something right there, because 3 is probably right there. And so that's probably the outlier is what that is. But overall, the residuals look good, because remember now, you probably will remove this outlier. When you remove this outlier, it won't be here. And now you've got your nice pattern here, okay? But let's look at some possible output that you might get. Again, this one is where we kind of have the assumption met. You see, we have the green arrow. But look at this one. Look at this one, okay? The residuals are kind of very shallow here, few and far between, but then they even start getting wider as we go further to the right. And then they're mostly here, wider here than here. You see, it's almost like a little diamond shape. That lets us know that we violated that homoscedasticity assumption. We could see here, if we would try to impose a line, that's curvilinear. It's a nonlinear relationship. Here, heteroscedasticity and nonlinearity. So you can kind of look at these things visually and say, doesn't look like it was met or something, and make a determination, okay? Now, what if violation exists? We're not going to spend a lot of time on this because, unfortunately, individuals get alarmed. Oh my, I've got to go back and do data collection again. And no, you don't. Because first of all, you're following the process. You're telling us the shape of the data. You have to do that. And then again, now, based on this shape, you're going to make some decisions. Okay, does that make sense to everybody? Now, yes. Now, one of the major decisions you can make is everyone's probably heard of transformations, right? Transforming data. perhaps taking a variable and squaring it or cubing it or running some logarithm of it, etc. You know, statistical math-orientated textbooks tell you that. That's a mathematical statistician's way that they would deal with that versus a applied statistician. All righty? When you run a process called bootstrapping, and you'll see just how simple it is, it helps combat those violation assumptions. Now, how does it do that? How does it do that? It's kind of giving you a statistical correction. Behind the scenes, the mathematicians are doing some things, and you don't need to worry about the math of that. But really, all they're doing is calculating some wider confidence intervals, okay? And you're basically adjusting the confidence intervals. In other words, if all the assumptions were met, let's just say that this was the range, the lower limit, this is the upper 95% confidence interval. The data looked good, it met the assumptions. We're pretty confident that the true results fall between here and here. What it will do is that it will still give us the same information, our slopes that we'll look at, but it widens the confidence intervals. In other words, making us less certain. Does everybody understand that? And we have to report those results. We did not meet the assumption, so therefore I'm reporting the worst possible condition. Can you understand that? Does everybody understand that? You don't need to go collect new data or anything. We're going to report 95% confidence intervals for some things. Now, that's a lot easier than transforming data because you'll see what this is just a matter of pressing a button. Okay? Now, we've done that and we've decided that, but let's look at the bootstrapping technique. Yes, I have a slide on that, how simple it is. In the linear regression process. Now, here's an example of what we call multiple regression because I have more than one independent variable, but it would be the same thing, okay? Here. But notice that over here, there's going to be a bootstrap button, okay? And when you click that bootstrap button, you make sure that perform bootstrapping is highlighted. 1,000 samples is okay. Make sure 95% confidence interval, and you hit continue. And then what happens is that what bootstrapping is that it's going to go into that data set and resample 1,000 times. And as we start resampling, data starts, showing us a normal distribution and things just seem to magically start happening to data. But that's more of a scientific concept. So don't worry about that. But bootstrapping then says, okay, now based on the data, the confidence intervals are wider. In other words, like in elections, the margin of error. A regular margin of error might be from 3 points to 5 points. But if we're not quite as sure, there's a lot of undecided, that margin may be from 6 points to 9 points. Do you see that? It's wider now. We're not quite as sure. Because the data's not quite there, perfect like we want it to be. Does that make sense? I really want to make sure that all these concepts make sense. So again, that we're easing anxiety. And when we see these things now, we have some understanding. Now, of course, we'll go back to the slides, the presentation, the recording, etc., but it won't be Greek to you conceptually of what you have to do. So if you would even see an application assignment in the course that says run multiple regression, be sure to address the assumptions, etc., that's not Greek to you anymore. It's not Greek, okay? Hopefully. Now, the normality is assessed by what's called a normal probability plot. The black line, and you see black and blue in there. The black is a solid black line running in there, but the little dots are kind of what the predicted values are. And you see they're hovering almost in a very good straight line. But now I superimpose this other red line here on here. And if a line looked like that, all the space here is letting us know that the data is deviating from normality. Okay, you see that? So just by looking at that, we can get an indication, of how the data should look. So what we're seeing is that everything we look at, residuals, be it for normality, be it for linearity, we want everything to be kind of tight. Everything to be kind of tight instead of being wide. Now, let me give you a very real life example that hopefully everyone can relate to. Think about, I live here in Northeast Florida, St. Augustine, Florida, and we're always on the lookout during hurricane season. The first thing I do in the morning is get up and look at the news and see what the weather's forecasting. And you'll see in the news, and you've seen them before, they're showing you all of these spaghetti plots, how all of that, and these are all different models. And they're saying, oh, the European model, is saying, the hurricane is going to hit, tomorrow at 8 a.m. This model, you see, and they're always telling that. So now let's go back to residuals and differences. Which model do you want to be correct? The one that comes as close to being to the date, the time, the place that things hit, right? That's what you want. So the residual should be very low in a prediction model. So hopefully that real live example kind of brings it home. All of these are different regression models that they're running, perhaps different variables in each model. So where Donald says that the European models are always better, perhaps they are really understanding the data better and what's really used and what's helping predict, that outcome. So that's what's happening, okay? When you see those spaghetti plots now. The next time you see one, I want you to yell out, regression, okay? And do that for me. Let me know you did that. Now, again, here's just an example now of, again, the bootstrapping that I wanted to show you. And don't worry about this output yet, because we're going to get to that. But basically, we have something called a slope. And as you can see here, this is 48.195. But notice that over here, the lower confidence interval says 45.432. So a little less, 45, than 48, and a little higher, 50. So those are that, what we call 95% confidence interval for this particular slope here. Now notice when we run bootstrapping, just by pressing that button, notice how the 45.1, the lower end, is now a little lower than that one. So in other words, it's wider. And say the 51.2, that was only 50, so it's even wider out that way. So that's all you would do. You would report just this table, something like this, saying because assumptions were violated, I'm reporting the bootstrap coefficients. That's all you're doing. Okay, don't get alarmed that you have to go recollect data, nothing like that. Are we good so far?
Please, I have a question
Yes.
that I put in the chat. So why did you choose the 1,000 samples when you
It default, good question. It defaults to that, but it doesn't matter. You can choose 10,000. Now, the thing about that is that this is a very labor-intensive process. Now, someone with let me just say, not an up-to-date and not up to speed and not all the RAM and speed in the computer, you try to do 10,000 bootstrapping samples, your computer's going to lock up for a while running that. Now, the more samples you use, the tighter your confidence intervals will be. More samples are better, but there's nothing wrong with using 1,000. It's just, it defaults there and it shows you made an effort to do something, and I'd be good to go with it. I wouldn't put too much other thought in that, though, but very good question. Okay.
Base that number on how many samples we have.
Excuse me?
So if we were to run that and we only have 500, say we only have 500 in the sample.
No.
Should we leave it at
That's not what
change it?
bootstrapping. No, that's not what bootstrapping is doing. If you only had 10 people in the sample, it's going to go in there and run 500 different samples from that 10. Okay?
Okay,
That's
okay,
what it's doing. So you got a data set with 1,000 people in it. It's going to, every time it's doing something, and we don't want to get into the science of sampling, but sampling by replacement. It goes in there, takes a piece, pulls another piece, puts it in there. This has been shown to be a proven statistical techniques. It mirrors Monte Carlo simulation studies. So I don't want to get into all that, but again, if you have violations, violated assumptions violated, you can run bootstrapping versus transforming the data. The other thing that transforming does is that it takes the data out of the original metric. So let's just say you have to run the 10th logarithm of a variable. How are you going to present data talking to a leader, a business leader about their dollars, about their satisfaction score, and you're talking in logarithms? It makes no sense. So that's why the mathematician would run a transformation, and to me, the researcher would run bootstrapping. Does that make sense? Okay, fantastic. Now, with all the conceptualization out of it, basically, knowing that we have to run preliminary tests before we do the analysis, let's look at the analysis now, and let's look at what it would look like. Now, the first thing I'm going to do now is I'm going to switch my screen and go into SPSS, and hopefully you all see an SPSS data file, yes?
Yes.
Now, here's a data file, and the research was done. Somebody collected a lot of data. Now, what I'm in is called the variable view. Okay, down here in the bottom, I clicked on variable view. And as you can see, I have an optimism variable, total optimism, and I have a life satisfaction variable. Okay? Now, each variable has a measure. I'm going to actually move that over. Remember when I started out the presentation on the scale, the scales of measurement? This is where you have to have that correct in SPSS. Optimism is that, remember we said scale. So you have to make sure that when you click in this box that you select scale. Or if you're using a data set, that if you are going to do a bivariate regression, you select a variable that has a scale measure. Does everybody see that? If you select the nominal and all these other types, that's really not the ideal data for the regression, okay? So, but these are the two variables of concern to us. Now, let's look at the data view. Optimism, right here. Person number 1, person number 2, person number 3. So in other words, person number 1 has a satisfaction score of 23. They have an optimism score of 22. So you see everyone differs in their scores. And what we're trying to do now is model this data. That's what we're doing, modeling. Okay, if we take this data and model it to see what kind of trend line it draws, what would it tell us? Where would something be if someone's score was 20? You see, that's what it's able to do. So it would compare this actual value to a true value, and it'll make a little bit more sense later. But I want you to understand this from an SPSS perspective too. These are the two continuous variables of concern. Okay? Now, what we would do is that we would go analyze regression linear. Okay? Now, this is the same thing that you would do for, say, multiple linear regression, but you are only going to put one independent variable. Remember, there should only be two variables here. So we know that we said that the dependent variable was satisfaction, and we're putting that in here, and we wanted to predict that from optimism. Okay, so let's just take a minute and look at that. Okay, the dependent variable, remember when we write the research question in temporal order, what is the relationship between optimism and, after the word and comes the dependent variable. So that's why I want you to see that relationship there. So when you start putting this in, you're seeing how this aligns with, say, your proposal or something of that nature, if that makes sense, or the research question that you wrote. Okay? Now we can get in here into some statistics, that we want. Always get the 95% confidence intervals. Remember, didn't we see Durbin-Watson before somewhere? Case-wide diagnostics, outliers. So it's all right here. I take descriptive statistics. You continue. Here's the bootstrap button right here if you needed to bootstrap. Okay. You see how it defaults to 1,000? Just leave it at that. That's all. And you simply hit OK. And this would be the results of that binary logistics regression. And we're going to talk about this, okay? Now, where we'll talk about that is in the presentation. And I'm going to make this a little bigger here. Now, what does all this mean? When we read those journal articles on regression, this is what's important. This is what is very important. Now, what does it mean? So here's the output. You hit the go button and SPSS starts spinning and this comes up. These are the major components. You could probably print over 50 pages of output in regression. We don't need all of that. So let's talk about the basic stuff here. The first thing you want to know is that variable significant predictor of life satisfaction. Where you find that information that is in the ANOVA table, okay? And in the SIG column. Does optimism significantly predict life satisfaction? You tell me. Yes, it does. There's the answer to your research question in very simple terms. That's it. Yes, it is a significant predictor. But unlike last night when we did correlation, we're going to look at now a little bit more information. We're going to start learning more about this relationship. There are some very important pieces here. One of the most important is this beta here, and we call that the slope. 0.317 for life satisfaction. Perhaps the most important thing to understand and interpret in regression. What does that mean? That means that for a 1 unit increase in the life satisfaction score, that would result in a 0.317 increase in total optimism. Does everybody see that? I'm going to do that again, okay? Here's the slope of 0.317, okay? What that means is that for a 1 unit increase in this variable, so let's just say that one person scored a 15 on their life satisfaction instrument. If a person scores a 16, that person is probably going to be a 0.317 higher score in optimism. You see, for that 1 unit increase, every 1 unit increase in how that instrument is being measured. Does everybody understand that? For example, if that variable was age, we're saying that for every year you age, your output variable is going to increase by 0.317. So in other words, and it's a positive number too, 0.317. So in other words, as we get older, as our life satisfaction goes up, as our life satisfaction goes up, this is saying our optimism goes up. Now think about that, back in my days when I was studying psychology, we always administering instruments to individuals, this test, this test, this assessment, this assessment. And so what this is saying is that I could use regression to say, okay, when I get an individual come in here and I get a certain score from that person, I know that the next individual with a higher score, 1 point higher score, or for every 1 unit increase in that score, that person is going to probably have a much higher outcome. You see what I'm saying? This is how now the practical application. So think about this in terms of your research. What would that mean? What does this mean in terms of narrative? How would you write this? That's what we have over here on the right. Okay. Now, what we have here, what I'm going to do now is I'm going to show you what all of this statistical notation means here, okay? And where it comes from. Now, so isn't this what we did? We conducted bivariate regression to examine its satisfaction, which was the predictor, right? Was a significant predictor of optimism. Or did I get that mixed up? Yeah, of optimism, okay, amongst Walden students, okay? And then I just further spell it out. Satisfaction was the predictor. Optimism was the dependent variable. Remember, it's telling me this all right here, okay? Preliminary analysis were conducted. Remember, this is where we assess the outliers. And to assess the assumptions of, and then I just listed them here. And I just gave you an example where, and I just said no violations were noted. Okay, that's just an example purposes. Okay, you may have had an outlier that you removed and you tell us that there. Now we're ready to run the results or present the results. So the results were significant. We know that, remember, from the ANOVA table. And you see the 1 in the 433 here. Anyone want to take a stab at what that is? What is the 1? Anyone? Yes, it's the degrees of freedom, but what does that mean? And tell me something in English terms that I can understand what that is. That 1, that gives you an indication of the number of predictive variables in the model. We know there's only 1 predictive variable in the bivariate regression, okay? If you were to see something in an output like that with a 4 in it, you know that's multiple regression because it had more than 1 predictive variable, just for tidbits, okay? 433, anyone want to take a stab at that?
N minus 2, N minus 1.
Yeah, it's a degree of freedom, but again, in English terms, we know that that 1 is a variable, tells me 1 variable. What does 433 tell me?
The number of cases we had.
Exactly, the sample size. It's an indication of sample size. Now, what that is for regression, I believe it's N minus 1. So you see it says 433. So you would know that the sample size is 434, something like that, 435, somewhere in that neighborhood. But you see the 1 in the 433, that's where the 1 in the 433 come from the regression and the residual degrees of freedom. Everybody see that? But remember now, this is not just Greek numbers to us. That 1 tells me that in this model, there was 1 predictive variable and there was a sample of about 434 people. You see how informative this information is now? It means something now. We're turning this into words, into narrative. Now, then we just report what the F statistic is, and that's just the mathematical calculation that was done, 131.832, okay? The next thing that's very important in any parametric test that we report is what is called the effect size, or the R square. That's going to come out of the model summary box. It's right there, 0.233, and I just put 0.23. What that is, that indicates that 23% of the variance in optimism. And what we do is that we take that and turn it into a percent by just moving the decimal place 2 places to the right. And it indicates that 23% of variance in optimism is accounted for by the satisfaction variable. That's a pretty good effect size. 23% of us understanding, in essence, satisfaction, can be accounted for by, understanding optimism is accounted for by satisfaction. That's very good in the social sciences. So do you see now what that's telling us? That's a lot of good information. And then I always like to see a statement that then just says, well, the null hypothesis is rejected and the alternative is accepted. And then, you'll have a table for descriptive statistics and a table for the regression summary that I'm going to show you, okay? But then what's important is, how do we predict? How do we use that? There's a formula. And this is important. The regression formula is y equals, and y is optimism because we're trying to predict optimism, right? Y equals 15.025. Where does that come from, Dr. Taylor? Look at the constant right there, 15.025. That's kind of like the starting point. Plus, how much will it increase? 0.317. And then we would input the person's satisfaction score, and that would give us an optimism value. Now, let's look at this way. I'm going to put this document in the course for you too before we leave. And yeah, here it is again, but no, maybe it's in the PowerPoint here. Let me look at something here. Yeah, here it is. Now, here's a slide right here with the regression equation. All this is the same information we just looked at before. Remember, this will show us the sample size. Remember the 434 and the 1, 435. It used 435 records, okay? So very close to the 434. Remember the R-square value. Remember the overall model is significant. These are the slopes right here. Now, let's put it into the equation. So y equals 15, which will always be the slope or the constant, okay? We have a positive slope plus 0.317 times whatever optimism is. Okay, excuse me, times whatever, I'm sorry, that would be life satisfaction. Okay, so let me make that change, because life satisfaction is the predictor, okay? Now, let's just do the math. One comes in and says that their life satisfaction score is 20. I just did the math. We know that their dependent variable, their optimism score is around 21.3. You see that? That person comes in and doesn't even know that. And let's just say me, I'm a psychologist. As a counselor, I'm working with people on optimism and positive psychology, et cetera, et cetera. And if this model works well, the sample was well, it represents the population, I can pretty much know where his optimism or her optimism would be. You see what I'm saying? Based on that predictive variable score. Because the model parameters have already been determined for me. My starting point and my increase per 1 unit of an increase in satisfaction. So let's say satisfaction goes down to 15. Of course, life satisfaction will go down. The math applies. Does everybody see how that formula is applied and where it comes from?
Yes.
Fantastic. That's what it is, but that's how it's useful, okay? So that's what all of this stuff means. Again, here are your confidence intervals, We know now that the true lower end would be 13, so it'll be a little bit to the left here. And the higher end would be 16, a little to the right, the 95% confidence interval, okay? So that's how you start looking at this and understand that. The F is the F statistic that was calculated. The ANOVA creates an F statistic. Don't worry about that. What you're going to be worried about is that that F statistic is significant. Okay?
Okay, thanks.
Yes. Does this make sense to everybody? A little bit more sense now than just looking at something and like I have no idea what I'm looking at and how to turn this into words and talk about my variables and what I talked about in my literature review and in my introduction and in my problem. You know, okay, yes, is it a significant predictor? How much does it, what value does it add in predicting? That's the value that bivariate regression can give you over, remember, folks, last night, all we did was able to just say one's related to the other, but it gave us no detailed relationship information. So as we get into the regressions, now we start getting more information. And all we'll do when we do a multiple regression session is we'll see that we have more independent variables. And we can see the contribution of each one in the model. Okay. Yes, satisfaction is the right variable. You're multiplying that by your predictors. You're trying to predict. This is Y is your dependent variable. That's the optimism right there. Satisfaction is the slope here that you're using in your formula. You use these in your formula here. Okay? So now, if we were to go back to our very first slide, let me see here.
Please, can I ask a quick question?
Yes.
Please, when you're looking at the case-wise diagnostics again, what are we looking for? I'm so sorry.
Outliers.
Okay.
Outliers. Remember, we had a whole slide dedicated to that. So in this case, it's saying here, probably case number 78, number 81, and 276 are outliers. Remember, they exceed the plus or minus 3 standard deviations. You see that? They're slightly above, and this is slightly below the 3 threshold, which gives us indication that there may be some outlier concern there. Okay? So again, you know, the other slide will show you how to go through each of these and understand what this all means. So now, if we were to go back to this first slide, would we say that without even talking about all the specifics and click in, click that, have we done a little bit of easing the anxiety behind this test? I'm just curious.
Yes.
Yes, you see it now, you understand, you say, I know that means something now. And I can go back to the presentation and the recording and see that and understand that. But now it's in English, what I mean, in narrative English spoken terms. And that's the key, looking at all of this output and understanding what does that mean. And you'll start seeing that as you progress through statistical tests, that it's the same concept almost. You're going to be looking for significant values, and every test has something, it means something different, but you'll see it becomes very easy now to start understanding when you read journal articles and critically analyzing those studies. Now you're able to critically analyze an article. Suppose you did a quantitative study and you looked at the statistical notation, where might that be? And suppose in something like this, the degrees of freedom here was 12. 12. What would that tell you? What would you say about that study if you put that in your literature review? What would you say about that? I'm sorry, say that again.
The study's underpowered.
Exactly, more than likely, significantly underpowered, more than likely. You know, very small sample size. So you see now, you critique, that's what you have to understand to be able to critique a study. So now why is that important? Because you definitely would not go into the study using 12 people, right? So you use the literature to help you make decisions, but you know that, hey, I'm looking here, what, a sample of what? I know it should be somewhat more than that. And this is where you start now critiquing the literature and understanding. And then saying, well, let me not make that mistake in mind. Let me make sure my power analysis is correct. And it says I need 80 people, and let me make sure I get 80 people, or whatever the case may be. All righty. So now let's talk about some additional resources. There's a host of quantitative resources from the Office of Research and Doctoral Services, our website, that you can go to at this link. Please take a look at that scales of measurement video tutorial. It's so important in all of your statistical analyses to understand. And then there's an outside link. Lead Statistics has a resource on bivariate regression. And we're going to take a quick look at these three sites. And I'm going to start putting some resources in the chat for you. So let me see if I kept any of that stuff open, and I guess I didn't. The first link that I provided, if I'm correct, let me look at the PowerPoint again. Yeah, quantitative seminars. That first thing is going to take you to this page, okay? Save this link as a bookmark, because as you can see, all of the upcoming seminars are here, okay? And when they're completed, they will move down here as a recording for you to have. And a list of recordings. I know someone last night asked the question of, do we have anything on meta-analysis? And I was like, you know what? We sure happen to have something there, okay? So here's some things on power analysis for certain tests, etc. So make sure you bookmark this. So now, this one that we conducted, the Pearson's correlation, that will move down here by tomorrow, hopefully. And even this one will move down here, and hopefully the schedule will be updated, okay? And these links are to seminars, just like we're conducting here tonight, live seminars, okay? Kind of using the same format. The other one's the scales of measurement specifically, but that video or that tutorial is listed here, you know, in our website. And then the other thing that I wanted to take you to, and I'm going to give you a resource on. Okay. What we just did is called linear regression. Remember the next step up after correlation. And there's a resource and a link, and they have some very basic information. But you notice we talked about the assumptions. It tells you about the assumptions, just as we talked about, should be continuous, a linear relationship, outliers. Remember all the things we talked about, the independence, you know, residual errors, etc. An example here is presented for you and how to go through the process in SPSS, okay? Again, analyze regression, linear. You know, you'll get this dialog box. You'll put in your predictive variables, your dependent variable. And remember now, we went a little further because we put in some other things when we clicked on the statistics and start clicking the things for our assumptions, you know, our case-wise diagnostics, our Durbin, Watson, and perhaps they don't have that listed here as such. But then you can see, no, maybe they do. But then how you can see the output of the regression, okay? Just like we talked about, okay? Remember the R-squared value, the ANOVA table, saying that this was a significant model predictor, and the predictive variable was income right here. And they were predicting price or something. Here's the regression equation. See that? 0.8287, again, which is the starting point, that slope right there. And you see the slope for income is 0.567. Well, excuse me, 0.564. You would simply put the income value in here, do the math, and whatever they were calculating would give you the predicted price. Okay, so now let me do this. Let me go ahead and look in the Q&A here for a second. PowerPoint. Mhm. Okay, how do you determine which variable is the dependent and the independent variable? Well, if you're just doing coursework, you're just going to have to select two and make a decision. If you're conducting your own research, then that's you getting into the literature and identifying the problem that you are going to be researching. Your problem is your dependent variable, okay? Then you'll have to figure out what predictor variables you're going to use, okay? So that's based on your research. One researcher may be concerned about satisfaction. Another researcher may be concerned about depression. That's the researcher's call. That's then becomes the dependent variable. Okay, does that make sense? Okay. Now, let me go ahead while I can, I'm going to go into the chat here. And so the first thing I'm going to start doing now is putting some documents in the chat. So I'm going for the PowerPoint now, okay? So we'll get them in one at a time. Chat, where are you? There we go. Okay, now for everyone we're checking the bottom of the chat, it should be a multiple linear regression PowerPoint, okay? So please check, make sure. Now the next thing I'm going to do is that I told you I had a Word document. And this Word document here is the same thing that I had on the PowerPoint presentation, okay? But it's in Word format. And the beauty of this is that, and this is the exact same information we looked at, but I was able to put a descriptive statistics table, and you report the means and the standard deviation for scale variables. There's the optimism. So the average score was 22.1, satisfaction 22.4, etc. And then a regression summary table is required for the regression. And remember, this is just from the SPSS output. Remember, that's that slope for the constant, the slope for satisfaction, etc., etc. And that's pretty much a complete. Here again is a research question: relationship between satisfaction and optimism, your null and your alternative hypotheses. The results, remember, we always look at the preliminary analysis first, which are our assumptions, okay? Then we run the results, and we know now how to look at SPSS output and make the correct statistical notation in our APA results write-up. And now we understand how the formula is used to help us predict. Remember, that's what we're trying to do, predictor. And it gives us some predictive value here. Okay? So let me get that in the chat also. Okay, take a look now. It should be a bivariate regression Word document, okay? Now, the next thing, even though you have it on the slides, I'm going to put the link in here to the live statistics also into the chat, okay? So I'm going to copy. Okay, chat, where are you? Okay, everyone check and make sure that you see the live statistics link now also, okay? And there you have it. That's binary regression in a nutshell. And if you understood this and just have a good conceptualization, you understand multiple linear regression, because the only thing is that you would have more than one predictive variable. Everything else is exactly pretty much the same. Okay. So are we good to go? Does everyone feel a little bit better? Now, the other thing that I'm going to encourage you to do is, if you would please,